Bam!
Mr. True. All right, in this lesson, we're going to be taking a look at the alternating series test, where we have the statement, let a sub n be greater than 0, the alternating series, where we have the summation where n starts at 1 and goes to infinity, of negative 1 to the n times a sub n converges if, and I always find this interesting that this condition is part of this conversion test, let the limit of a sub n, the limit as n approaches infinity of a sub n is equal to 0. What is this, Andy? It's the nth term test. If the limit as n approaches infinity of a sub n is not 0, what does the series do? Diverges. So this is arguably the first condition of every convergence test, but it's specifically stated for some reason in the alternating series test, so I'm going to keep my notes consistent with the book. And a sub n plus 1 is less than or equal to a sub n. So the sequence is monotonic decreasing. What you're looking for in the expression that is behind your sigma notation or your summation notation is a negative 1 to some power. Now, there are powers that are always going to be even, like even or odd. If we have negative 1 to the 2n, what's the sign of that answer? What's negative 1 to the 2n where n is an element of positive integers? Because that's the domain of basically sequences. It's going to be 1 because any number multiplied by 2 is what? Even. If I do a negative 1, so that's going to be equal to 1. If I do negative 1 to the 2n plus 1, any number multiplied by 2 is even. And then when you add 1, you get odd. And negative 1 to any odd number is what? Negative. So as I come over here and I point to this notation of we have the summation where n starts at 1 and goes to infinity. N can start at 1, 2, 5. I mean, we can negate some of the early terms of a sequence or series and still determine its convergence, because the behavior of convergence of a series is about n going to infinity, not the first few terms. I'm writing negative 1 to the n. First of all, I'm showing that a sub n is kind of pulled away from a negative 1 to some power. So even though I'm talking about a series where the terms are going to alternate between being positive and negative, this is, by the way, like our p-series test or integral test or, I'm forgetting something, or limit comparison test or direct comparison test, all those tests have a condition that every term in the series, excluding maybe a couple of initial terms that we have to exclude, after some value of n, every term in the series is positive. So that condition does not exist with an alternating series test, obviously, if we have negative 1 to some power. Now, we're going to identify a sub n as the factor of that general term that is always going to be positive and look at the negative 1 to some power separately. You could have a negative 1 to the n, a negative 1 to the n minus 1, a negative 1 to the n plus 1. You know, this exponent on the negative 1 base can vary. Just not vary in such a way that you have a constant sort of positive or negative answer. That wouldn't make any sense. It wouldn't be alternating. We're going to be sometimes looking at the actual individual terms of a sub n plus 1 and comparing them with a sub n and being able to show that that's a monotonic decreasing sequence of numbers creating a series. Or at times we'll be writing out functions that sort of agree with and are proper functions that agree with that general term of a sub n and doing like finding a first derivative and seeing if that first derivative is always negative. After a few examples, we're going to be talking about an alternating series remainder. There are only 2 series that we learn in this chapter that you can find not only whether the series converges or diverges, but if those 2 series converge, you can actually find the series or the infinite sum. What are the only 2 series you can find the infinite sum for? Geometric and telescoping. Your integral test, your p-series test, your direct comparison test, your limit comparison test that we've done so far, we do these tests to determine if the series converges or diverges, and a lot of times we're just left being able to say, yes, the series converges, meaning that this infinite sum approaches some real value without actually finding or being able to find that infinite sum, that series. Well, we can't exactly find, if you will, with limits, the value of the series if our alternating series does indeed converge, but we can estimate it. So our alternating series remainder says if you have a convergent alternating series such that it satisfies the condition that a sub n plus 1 is less than or equal to a sub n, and this is what your textbook says, which again is kind of redundant because that's basically the condition check for the alternating series to converge. But we have here the absolute value of the difference between the infinite sum, remember S is infinite sum or the series value, minus S sub n, which is a partial sum. So we can take a finite set of terms, find the partial sum, and know that the difference between the unknown infinite sum, the series value, minus the partial sum, the absolute value of that is equal to the absolute value of the remainder, the difference. And that remainder, and the absolute values are in here because we have, we're talking about alternating series. We'll have positive and negative terms. That remainder is going to be less than or equal to, now I just like to, it's redundant, now I'm putting some redundancy in. That remainder, the absolute value of that remainder, the absolute value of the difference between the infinite sum and partial sum is going to be less than or equal to the first neglected term. You see this is a sub n plus 1. So if you find a partial sum with 4 terms, that's going to be R sub 4, indicating that it's a remainder, the difference between the infinite sum and the partial sum of 4 terms. That difference is going to be less than or equal to the absolute value of a sub 4 plus 1, or the 5th term. The reason why I'm saying that the absolute value around this a sub n plus 1 is redundant is back up here in the initial notation. We are going to have terms in our series that alternate between positive and negative, but the notes, the textbook, we are defining a sub n as the positive factor of that term and pulling and identifying, working with that negative 1 to a power as a separate factor within that one single general term. So arguably the absolute values around a sub n plus 1 is not needed. I just like to write them. Okay? Makes sense? The test itself is really nice. It's quick, usually, if we don't have to work with a derivative. So let's take a look at our first example. We have determined the convergence or divergence of our series where n starts at 1 and goes to infinity of negative 1 to the n plus 1 over n. This is our example, but I might have just negative 1 to the n. I might have negative 1 to the n minus 1, or like we have here, negative 1 to the n plus 1 power over n. Our final answer of whether or not this series converges or diverges will be the same. We can see here that we do have a negative 1 to a power that's going to allow the terms in this sequence to alternate. We're not going to have just like maybe the first or second term that's negative, but throughout the entire series, we're going to have positive and negative terms. So this is an alternating series. A sub n is going to be the factor in this general term that is not alternating. So we could, I'm just going to write this for notes. Wouldn't think anybody in here would have to do this more than once. This is going to be the summation where n starts at 1 and goes to infinity of negative 1 to the n plus 1 times 1 over n. I'll be talking later on in this lesson about the difference between absolute convergence and conditional convergence. So we're going to look at this example a second time. But for right now, we have a sub n is equal to 1 over n. And to just do all these nice formal conditions, every time you do any convergence test, the first thing you should be doing is the limit as n approaches infinity of a sub n, which is our 1 over n, and make sure that that approaches 0. And I think maybe this is included because it is an alternating series and they're indicating you have to pull the positive factor out individually. maybe that's the justification as to why that's there. What's the limit as n approaches infinity of 1 over n? Yeah, it is 0. This is your reciprocal function we learned in pre-calc. We know there's a horizontal asymptote of y equals 0. Our second condition is we need to find a sub n plus 1 and make sure that it's less than or equal to a sub n. And I like to do this example like I taught you how to do the squeeze theorem that we revisited when we did the direct comparison test, which is to say that don't look at a entire fraction in its totality, but look at the part of the fraction that's going to be different and then bring in the common numerator and or denominator. So is it true that n plus 1 is greater than or equal to n when n starts at 1 and goes to infinity? Basically, n's a positive integer. Well, of course it is. So then, since these are two positive denominators, it would make sense then that 1 over n plus 1, when we compare that to 1 over n, this denominator is larger, which is going to make this entire fraction what? Less than or equal to. So therefore, we have shown that a sub n plus 1 is less than or equal to a sub n. Therefore, by the alternating series test, the given series converges. So we just showed that, even though I am going to revisit this shortly, we just showed that this series, by the alternating series test, converges. If I cover up the negative 1 to a power and talk about and highlight this series where n starts at 1 and goes to infinity of just 1 over n, what's that series called? That's harmonic. So without the alternating factor, the harmonic series diverges, whereas the alternating harmonic series converges. So I'm just going to say it now so I can repeat myself later and maybe kind of like sinks in a little bit more. The alternating series converges by the alternating series test, but the absolute value of that alternating harmonic series, which is the harmonic series, diverges. That's going to mean we're going to be saying later on that this series is conditionally convergent, where the alternating series converges and the absolute value of that series diverges. That would mean that your alternating harmonic series is not just convergent, it's conditionally convergent, as opposed to the stronger absolute convergence. So we'll look at that a little bit later. Okay, so for our second example, what's a sub n in this? We have a negative 1 to an n power. So we're going to, when n is 1, we're going to have a negative term. When n is 2, we're going to have a positive term. When n is 3, we're going to have a negative term, and so on. What's a sub n in our second example?
Natural log of n plus 2 over n.
Awesome. What's the first condition check for an alternating series to be convergent? The nth term test. So test or check number 1, the limit as n approaches infinity of the natural log of n plus 2 over n plus 2. Now, maybe if you're given a question about does this series given converge or diverge, maybe you need to show some work about L'Hopital's rule. I'm going to do it for notes to remind us of what it is. I don't think you need a reminder. If this work is part of an even bigger question, which is finding the interval of convergence for a Taylor or Maclaurin series, you don't need to show every little nuance, every little tiny check, because there's going to be so much involved in the overall problem. But this is going to be, we're not there yet, so this is going to be in the form of, it'd be illegal to write equals, because we're going to probably find an answer later on. But this is in the form of what? What is natural log of n plus 2 approach as n goes to infinity? Yeah, that goes to infinity. What's infinity plus 2? Another infinity. This is a condition check to do what? L'Hopital's rule. I'm just going to throw you, all y'all are going to get points. I'm just keep yelling these out. These are good. So we're going to apply L'Hopital's rule, which you all know means that we're going to be taking the derivative of the numerator and denominator separately. So we have the limit as n approaches infinity, the derivative of natural log of u is 1 over u. The derivative of n plus 2 is 1 over n plus 2. The derivative of our denominators separately, individually, is just simply 1. And the limit as n approaches infinity of 1 over n plus 2 is indeed equal to 0. So we have passed the first condition check. Now our second condition check is to show that, and that is a condition check that I just erased, the infinity over infinity, to apply L'Hopital's rule, but I want to make sure I don't run out of room. Our next thing is to show that the a sub n plus 1 term is less than or equal to a sub n. Now, anybody ever use a ruler? A ruler, like a ruler, a regular ruler. Like, well, you know, an American ruler that has inches instead of, you know, lovely centimeters and meters. You might be looking at, say, 11/16 of an inch versus half an inch. And though this might be a super obvious example because I just made it up off the top of my head, what would we really need to do to determine which of these fractions are larger? If we didn't really know a ruler, you'd want to find either a common numerator or a common denominator. So I believe 11/16 is bigger, but I'm not really truly going to know that until I come over here with this other fraction and multiply the numerator and denominator by 8 and get some part of the fraction to be the same, whether it be the numerator or denominator. Like we had in the first example, it was obvious to say that 1 over n plus 1 was less than or equal to 1 over n, at least if n is positive. So here, a sub n is natural log of n plus 2 over n plus 3, natural log of n plus 2 over n plus 2. And a sub n plus 1 is going to be the natural log of n plus 1 plus 2 or n plus 3 over n plus 1 plus 2, which is n plus 3. And I'm sorry, even myself, I'd be hard-pressed to, you know, without a shadow of a doubt, state that this fraction is less than this fraction because the numerator and the denominators are different. I know the behavior of the natural log function and how it kind of heals over and starts growing really slowly, but it does never stop growing. So this is a little bit sketchy. Therefore, let's let f of x equal the natural log of x plus 2 over x plus 2. And is this going to be good to, you know, kind of let this function act like our general term, our a sub n term? We did point out a few days ago that you could have an issue where, you know, like maybe if you have a negative base to a power, like you could make a function that looks like your general term but acts all crazy once you analyze it. So you could like type this in the calculator, make sure it's continuous for n is greater than or equal to 1. Doesn't have any crazy behavior, but we're good here. So how do we determine if a sub n plus 1 is always going to be less than or equal to a sub n? This function has to be doing what? Decreasing, which means its derivative has to be negative. There you go. So let's find the first derivative. So f prime of x is going to be that we're taking the derivative of a quotient, so it's low. D high, the derivative of natural log of x plus 2 is going to be 1 over x plus 2. Well, that's nice. Low d high minus high, so the natural log of x plus 2. D low, the derivative of x plus 2 is 1, all over low low. So now we have our first derivative, f prime of x is, well, x plus 2 divided by x plus 2 is 1, minus the natural log of x plus 2 all over x plus 2 squared. This derivative needs to be negative. And it needs to be negative, you know, if we have to go to like an n value of 2 or 3 or 4 or even 10 for that matter, we can negate some of the early terms of our series. But after some value of n, after some value of x, this derivative needs to be negative. We need to figure that out. When does this turn negative? What's the denominator?
Positive.
It's something squared, so it's always going to be positive. Nice. So we just need to find out, since our denominator is always positive, where is the numerator negative? So let's subtract both sides by 1. And we have negative natural log of x plus 2 is less than negative 1. Divide by negative 1. Natural log of x plus 2 is greater than 1. Make both sides an exponent of e. And now we have x plus 2 is greater than 2.718. And subtract 2, and x has to be greater than 0.718. Well, that's great. I do like to, show my condition checks that kind of match the language of the series. And n is starting at 1, so really, I can say that f prime is less than 0 for x is greater than or equal to 1. Therefore, a sub n plus 1 is going to be less than or equal to a sub n for n is greater than or equal to 1. And by the alternating series test, the given series, what? Converges. Bam! This is fun stuff. Next example, which I don't know why I'm saying that because I have to write it out. For our next example, we have the alternating series error. We're going to take this series where n starts at 1 and goes to infinity of negative 1/2 n to the minus 1 and find the partial sum, find the sum of the first 7 terms, and then analyze r sub 7, the remainder. And this is not going to be really an example that you're going to have in your homework or on any kind of test. I'm going to do this example with a series that we can actually find the value of s. We don't need to estimate the series value for this. We can actually find it. Why? It is alternating. And for the integral test, the p-series test, the direct comparison test, the limit comparison test, all those have a condition where all the terms, maybe negating the first couple, are positive. What type of series is this? Geometric. Yeah, it's geometric. This is one of the 2 series that we can actually find the infinite sum for, the series value. So I'm going to use this geometric series to kind of like show or justify, certainly not a proof, but sort of like work through that alternating series reminder formula that says the absolute value of the infinite sum minus the partial sum is equal to, by definition, the remainder, the difference, r sub n. That's going to be less than or equal to the first neglected term, whether, you don't really need the absolute values there, I just like them, is going to be less than or equal to the first neglected term. So will be less than or equal to a sub 8. So since this is geometric, with r being equal to negative 1/2, the absolute value of that, which is less than 1, so it's convergent, right? How do we find the infinite sum? Okay, well, to do that, first thing you have to do is have a little bit of an expansion, which I think. When we let n be 1, we have negative 1/2 to the 1 minus 1, which is 0. And anything to the 0 power is 1. So negative 1/2 to the 0 power is 1. When n is 2, 2 minus 1 is 1, so we have negative 1/2 to the first power. So negative 1/2. When n is 3, we have negative 1/2 squared. So we get positive 1/4. When n is 4, I'm pointing down here where n is 1. When n is 4, 4 minus 1 is 3. Negative 1/2 to the third power, negative 1/8. When n is 5, we have negative 1/2 to the fourth. So positive 8 times 2 is 16, so 1/16. And then when n is 6, we have negative 1/2 to the 5th power, which will be negative. And that's going to be negative 1 over 32. Thank you, Veer. And then finally, when n is 7, we're going to have a plus 1 over 64. Now, if I stop writing, that's a partial sum. My upper limit on my sigma notation is infinity, so a little plus dot, dot, dot. Okay, what is this infinite sum? Which you basically will never be able to find on any normal, textbook or test question about an alternating series. What's the infinite sum of a geometric series? This geometric series does happen to be alternating, but it's a geometric series. You have to look that up? Come on. No. Oh, I'm disappointed. We just did geometric series. Come on, I brag about you all the time. It's a sub 1 over 1 minus r. Oh, that's right. Oh. So we've got 1 over 3 halves, which is 2/3, and just make sure I didn't do something silly. Okay, that is the answer. So now let's pretend like we don't know that s value. Let's pretend that we do not know that s, the series, is 2/3, that the infinite sum is 2/3. Let's find s sub 7. Now, this is, we have written out the first 7 terms. And if we just add those first 7 terms, s sub 7 is equal to, right off the top of my head, as in I did this years ago and have the notes saved on my iPad, 0.6718. So that's the partial sum based on the first 7 terms. Now, that means the alternating series remainder says that the absolute value of the series, which normally we do not know, minus the partial sum, only we do know the infinite sum, for this walkthrough example, 2/3 minus the partial sum of 0.6718 is equal to the remainder. And I'm writing all this and wishing I'd put the symbols up here. So what am I doing? I'm doing the absolute value of s minus s sub 7 is then going to be equal to the absolute value of r sub 7. In this example, because again I gave you a geometric sum, we're going to be able to exactly find the remainder. That is not going to be the normal situation. But what is the difference between, so I'm going to need some calculator help because I don't know if I have this, oh I do have this decimal. If you do 2/3 minus 0.06718, you're going to get the decimal of 0.0051. Now, again, our alternating series remainder says that the remainder, r sub, in this case, r sub 7, the absolute value of that remainder is going to be less than or equal to the first neglected term. So, Veer, you're doing a really good job of helping me out. We got up to n is 7. When n is equal to 8, what's the 8th term? What's a sub 8? Minus 1 over 128, right? Yeah. So a sub 8 is, now there is a minus there, but the a sub n, remember, is the positive factor. So a sub 8 is 1 over 128. So, yes?
Wouldn't there be a negative inside the absolute value? It's looking how positive. There is a negative.
You're right. Thank you. Thank you for the help. 2/3 minus 0.6718 is going to be a negative. That's why you need the absolute value. So we have that r sub 7. The absolute value of r sub 7 is the absolute value of negative 0.0051. And that needs to be, by our definition of the alternating series remainder, that needs to be less than or equal to a sub 8. Well, our a sub 8, which I wrote in orange, our a sub 8 is 1 over 128. So let's see if this checks out. The absolute value here gives us 0.0051. Is that indeed less than or equal to this first neglected term? 1 divided by 128 is 0.0078. So this is by no means a proof, right? You can't do proofs with numbers, but I'm giving you, we gave you this geometric series that did, for this unique problem, allow us to find the infinite sum. We found a partial sum of using the first 7 terms. Because we knew the exact value of the series, we were able to actually subtract the series value with the partial sum value and get an absolute value of r sub 7 to be 0.0051. And again, it's just an example. It's just a walkthrough, numerical walkthrough. But we can see that it is the absolute, this r sub 7, this remainder based on the first 7 terms, that remainder, that a sub 8, is greater than our remainder. Thanks for coming to get to school to get us all sick. Okay. You came just for me?
Yes.
Nice. High five.
Wait.
All right. Estimate the series. Let's estimate the series using the first 6 terms of this alternating series. And let's just assume it converges. Okay? So how are we going to estimate the value of the series? How are we going to estimate the infinite sum using the first 6 terms? What we're going to do is estimating a series, or estimating the infinite sum, is kind of like, sort of like in statistics we would have called it a confidence interval. Give an interval where you know the actual series value resides. We can't find the infinite sum. This isn't geometric like the previous question, but we can estimate it within a range. So what do you think the first step is?
Probably nothing.
What part of this can we find? S sub n. So let's find the sum of the first 6 terms. So when we let n equal 1, n equal 2, and these are going to be kind of like ugly numbers, so I'm just going to write this out. So n's going to be 1, 2, 3, 4, 5, and 6. And a sub 1 is going to be 5. A sub 2 is going to be 5/8, negative 5/8. A sub 3 is going to be 5, positive 5 over 27. And then we've got minus 5 over 64 plus 5 over 125. And then minus 5 over 216. When you add up these first 6 terms, we're going to get S sub 6 is equal to 4.499, clearly needing some calculators here. And to estimate within a range what the series value, the infinite sum, is going to be equal to, what's the next thing we have to do or find? The first neglected term. So we need to find a sub 7. So a sub 7 is going to be negative 1 to the 7 plus 1 power, or to the 8th power, times 5 over 7 cubed, which means we're looking at 5 over 300. I don't know why I'm surprised. 5 over 300 and 43. So it says here the absolute value of S minus S sub 6, so 4.499, that is the remainder, and that must be less than or equal to the first neglected term. So that has to be less than or equal to 5 over 343. How can I write this absolute value inequality so we do not have absolute values? Let's go back to the geometric series. If I say that the absolute value of r has to be less than 1 for a geometric series to be convergent, what does r need to be between? Negative 1 and positive 1. So if the series value, the infinite sum, s minus 4.499 has to be less than or equal to 5 over 343, then s minus 4.499 needs to be less than or equal to 5 over 343 and greater than or equal to negative 5 over 343. And then when you find the decimal approximation of 5 divided by 343, and to that you add 4.499, we get that S is going to be between, S is going to be greater than or equal to 4.4844 and less than or equal to 4.5136, which I would say is pretty astonishing that the idea of an infinite sum is to add up literally an infinite number of terms. And with this alternating series, just adding the first 6 gets us pretty darn close. That's a very tight, I would say, interval for which the infinite sum must be between. So that's we hone in, we get close to the infinite sum quite quick, pretty often when dealing with partial sums of alternating series. So this time I'm going to give you a few minutes with this example and 2 under our belt. All right, let's finish up this example. Determining the number of terms required to approximate the sum of the series with an error that's less than 0.001, where the series is the summation of n starting at 0 going to infinity of negative 1 over n over 2 times n cubed minus 3. Well, I've got it erased now, but let me write this up here again. For the alternating series remainder, the absolute value of the series minus the partial sum, the difference between those two will be equal to the absolute value of the remainder that is based on the number of terms, of course, used to find that partial sum, which will be less than or equal to a sub n plus 1. So we're finding that sum with a certain number of terms, and the remainder, the difference between the infinite sum and the partial sum, that remainder needs to be or always will be less than or equal to a sub n plus 1, your first neglected term. So if you want to make sure that your error is less than 0.001, if you want to make sure that your remainder is less than 0.001, then just make sure that your first neglected term is less than that value. So we're going to take n plus 1 and plug it into our general term. And remember, we are looking at that a sub n as the positive factor of our general term. So I'm not going to use that negative 1 to the n. And we have 1 over 2 times n, not n cubed, but n plus 1 cubed minus 3 needs to be less than or equal to 0.001. And we are going to, at some point, need to use a calculator for this, or you could just do trial and error right off the bat. But I'm going to show a few algebraic steps So I'm going to write this 0.001 as tenths, hundredths, and thousandths. It's going to be less than or equal to 1 over 1,000. And on my denominator here, 2 times n plus 1 cubed minus 3 will be positive for when n is greater than or equal to 1. So, yeah. So I'm going to multiply both sides by this denominator and multiply both sides by 100. And we're going to get 1,000 is less than or equal to 2 times n plus 1 cubed minus 3. Add 3 to both sides, and we have 1,003 is less than or equal to 2 times n plus 1 cubed. Divide by 2, and we have 501.5 is less than or equal to n plus 1 cubed. Cube root both sides, and right off the top of my head, of course that's not actually the case. We have 7.94 is less than or equal to n plus 1, or n needs to be greater than or equal to 6.94. Well, n, basically, right, is a positive integer. The domain of sequences and just how we're working through the summation notation. So n is going to need to be greater than or equal to 7. So we need a partial sum with at least 7 terms to make sure that our remainder is less than or equal to 0.001. And that's how you do that style of problem. So for our last example in the video, we're going to determine if this given series is absolutely or conditionally convergent. So what does it mean? What does that mean to be absolutely convergent or conditionally convergent? Well, not all series with negative terms are going to be alternating series. So if you expand out a sigma notation, a summation notation, and you see that there are sporadically some negative numbers within that series, and it's not an alternating series, or maybe they're all negative. One way to determine if the series converge is to analyze the absolute value of that series. So just take the absolute value of that general term, a sub n, to create a new series, and then determine if that series converges. If the absolute value of a sub n converges, then the original series, a sub n, is said to be absolutely convergent. Absolute convergent is like the strongest type of convergence when you have a series with some negative terms in its expansion and it's not an alternating series. If, however, you see that the series of the absolute value of a sub n diverges, you're not done. You're going to have to go back to the original series and determine if that series converges. So if the series a sub n is conditionally convergent if the series a sub n does converge, but the series where you have the absolute value of n, that diverges. And a really very famous sort of textbook, they all talk about this, are harmonic series. The series of 1 over n is a divergent harmonic series. It's that p series with the p-value of 1, and we proved that this was a divergent series earlier this chapter by using the integral test. However, we also, at the beginning of this, literally just in the beginning of this lesson, showed that if we have the series of negative 1 to the n over n, that is, with the alternating series test, a convergent alternating harmonic series. So at the beginning of the lesson, where we had the series where n started at 1 and went to infinity, of negative 1 to the n over n, we just looked at that series, did the alternating series test, and determined that it converged based on the alternating series test. Now, if we were given this alternating series at the beginning, and the question originally said, does this series converge absolutely? When you see in the directions, does the series converge absolutely or convergently? You are going to have to do, it's a sneaky way of giving you really potentially 2 questions at the same time. You will have to take the absolute value of n, determine whether that absolute value series converges or diverges, and if it converges, you're done. The given series converges absolutely. But if that absolute value of that series diverges, because the question specifically says, does this series converge absolutely or conditionally, you're going to have to more than likely do an alternating series test to finish up the problem. and look for that absolute or conditional convergence, like we're about to do. So I just erased my directions, so that was silly. But we have a series where n starts at 0 and goes to infinity of -1 to the n power over the square root of n plus 2. Does this series converge absolutely? Not just does it converge. That would just require us to do an alternating series test because of the -1 to the power of n, but does this converge absolutely? So let's take a look at the absolute value of the series, taking the absolute value of a sub n, and we get the series where n starts at 0 and goes to infinity of 1 over the square root of n plus 2. And maybe just do mentally our first check, which is the limit as n approaches infinity of 1 over the square root of n plus 2. Yes, that does indeed equal 0. So by the nth term test, well, if it was not equal to 0, we could stop and it diverges. But our nth term test shows that this limit does equal 0, meaning we just, we have work left to do. We can let f of x equal 1 over the square root of x plus 2 and determine convergence based on a integral test. Or we can compare this series to 1 over the square root of n, where n starts at 1 and goes to infinity, because we can't start n at 0, we'd be dividing by 0. And that is a p series. This is a divergent p series with p being equal to 1/2, which is less than 1. So this is a divergent p series. So again, we already had that option of determining if this is convergent or divergent by the integral test. If we compare it to this p series, now this is a divergent p series. So for this series to be divergent, we would have to show that it was every term of b sub n is less than every term of this a sub n after some given value of n to determine that this series diverges. But indeed, the square root of n plus 2 is a larger denominator than the square root of n. So every term in this series is going to be smaller than every term in this series. So this series being divergent prevents me from doing a direct comparison test. What we have to do is a limit comparison test. So we're going to do the limit as n approaches infinity of a sub n, which is 1 over the square root of n plus 2, divided by b sub n, which is 1 over the square root of n, giving us the limit as n approaches infinity of the square root of n over the square root of n plus 2. And in a large complex calculus problem, you're probably not going to actually need to do any kind of real work to justify this answer as 1 based on L'Hopital's rule or algebra. But if you wanted to do some algebraic work with this, you find the largest power in the denominator and divide that into the numerator and denominator. So multiplying the numerator by 1 over the square root of n and the denominator by 1 over the square root of n, we get the limit as n approaches infinity of 1 over the square root of 1 plus 2 over n, and that's going to come out to be 1. This is a positive finite real number. Therefore, by the limit comparison test, the series where we have the absolute value of a sub n diverges. Well, unfortunately, we're not done, because the question, which I erased the directions, remember, but we're not being asked to determine whether the series converges or diverges. We're being asked to determine whether the series is absolutely convergent. Well, we took the absolute value of the series, and we got an answer of divergent, which means we still have another problem to do, which is the alternating series test. I had all this recorded. It came out great. But I didn't have it recorded. Which now I'm like saying it for the second time in half an hour. So it's lovely because, you know, this isn't already a lot more work. So we already did the nth term test. So remember, we have a sub n is equal to 1 over the square root of n plus 2, and a sub n plus 1 is 1 over the square root of n plus 1 plus 2, or n plus 3. Now, we broke this down a little bit more specifically in an earlier example, but we can clearly see with these numerators being equal that a sub n plus 1 is going to be less than or equal to a sub n, because that larger denominator is going to yield an overall fraction that is smaller. So a sub n plus 1 is less than a sub n, and the limit of a sub n as n approaches infinity is equal to 0. Therefore, the given series converges by the alternating series test. And once again, the series of the absolute value of a sub n diverged. Therefore, the series given, the series of a sub n, converges conditionally. And that is the end of my last example. Bang! Go do your homework. Let's actually hope it's recorded this time. Now I'm done.